Okay, looks like we have a big integral on the board. We're integrating from 2 square root of 3 minus 5 to 1. We have dx over the square root of x squared plus 10x plus 25 times x squared plus 10x plus 16. It's kind of crazy they gave us this in the as a bound, but let's just not worry about that right now and think about this. And what I want to do is let's look into factoring this or getting this into a nicer form. So the first thing I noticed, these both look factorable, and I think what we can do, this first one is a perfect square. So let's just look at, this is going to be, if we multiply out x plus 5 squared, we get this exactly, okay? Now the second piece we can't factor quite as easily, but we can see the, because this part and this part are exactly the same, what we can do is we can look at this, we can complete the square, but we also could just say, if we take this and you subtract 9 from it, you get exactly that, right? Because 9, subtracting 25 minus 9, you get the 16. So this is another way to write this. But then because this is a perfect square inside the square, we can bring it out front of the radical. Typically we need an absolute value here, but because with our bounds, this is always going to be, this x plus 5 is always going to be positive. So let's just rewrite this. Okay, and then from here, now we notice we have our x plus 5 and x plus 5. We could do a u substitution, but what I'm noticing is this is in a format for like a trig substitution. This is in like the format where we'd want to do, use our secant substitution, just as the way it's set up. And so then we can actually just skip our u substitution and go directly to the trig substitution. So let's do that. So for my substitution, what I'm going to do, I'm going to want to do x plus 5. And like I said, we're going to want to use secant of t. Now the only thing is we have this isn't a 1, this is a 9. So what we want to do is if we use 3, then when we look at x plus 5 squared in this substitution, this is going to be 9 secant squared t. While I'm at it, I think I'll just solve for my value of t. So if we divide by 3, we'll have an x plus 5 over 3 here, and then we'll take an inverse. So we'll have our t is equal to sec inverse x plus 5 over 3. And we'll just get our dx by we'll take our derivative on this line. So we'll do derivative of x plus 5 is just going to be dx. And then this one's going to be 3 secant t tan t dt. And then we're ready for our substitution. So when we plug a 1 in here, we're going to have 6 over 3 is 2. So we're looking at sec inverse of 2. Well, that's going to be the same thing as cos inverse of 1/2. And that happens at pi over 3. And then here's where we get to deal with our messy boundary, 2 squared root of 3 minus 5. So let's just look, when I plugged it, let's just look at x plus 5 over 3. So if I take 2 square root of 3 minus 5, then we're going to have plus 5 over 3. Our 5's cancel, and we're left with 2 square root of 3 over 3. And then because we're going to want the secant inverse of this, it might be easier actually if I multiply this. Usually we rationalize the other way, but let me just multiply this by square root of 3 over square root of 3. Then we have 2 times 3 over 3 square root of 3. The 3's cancel and we have 2 square root of 3. So what we really want is we want secant inverse of 2 square root of 3. But then just to flip that, we're actually looking for, that's going to be the same thing as looking for cosine inverse at square root of 3 over 2. And that happens at pi over 6. Now for our dx value, we have that right here. So that's going to be 3 secant t tan t dt. X plus 5, we have that right here, 3 secant t. Okay, x plus 5 squared we have right here, so that's going to be 9 secant squared t minus 9. These terms are going to cancel. If we take out this 9, we can pull it out as a 3, so we can make this a 1/3 in front. And now we're just looking at this as secant squared t minus 1. But then notice we have an identity that this is actually the same thing as tan squared t. But then we have tan squared inside the radical, inside a square root. So that's just going to be tan t, which is going to cancel with this term in the numerator. We're just going to have 1. Tangent will always be positive within these bounds in the first quadrant. So then we don't have to worry about that absolute value there. So after all that, we're integrating 1. So we're going to have 1/3 in front. Integral of 1 is just going to be t. And we just have to evaluate this from pi over 6 to pi over 3. And then we're just looking at pi over 3 minus pi over 6. We could just write this as 2 pi over 6 so that this whole thing is pi over 6. So multiplying pi over 6 times 1/3, we get our final solution, which is just pi over 18. So that's it. Thought it was a pretty good problem. We'll stop it there. Thank you for watching. Please like and subscribe. Have a great day.